Okay, this is going to be the 2025 mechanics free response questions. We'll do one video for each question. In this first question, we have two blocks, block one, block two, sliding towards each other. Block one has a mass of M, 6M, 2 VO, and VO. The collision occurs during a time between TO to TC. So the collision takes some time to happen. After a collision, the blocks move together with the same constant speed. Let's adjust this a little bit. Go. So the diagrams in figure 2 can be used to represent the momentum of block 1 and block 2 after. So let's get that. Let's see how it's on the other side here. So there we go. Sorry, I'm going to have to flip pages over. And it says, draw arrows on the grids to represent the momentum vectors of block 2 before the collision and the two block system after the collision. And we know it should start at 0 and the length should be proportional to the magnitude. And then if it's 0, then we just draw a dot. So basically we're going to have this one, which is going to have a momentum of 2 mVo, and this one's going to have a momentum of 6 mVo. So let's see how they did that on this side. So this one had a momentum of 2 little tick marks. So this one's going to have a momentum of 6 little tick marks in the opposite direction. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So it should go like that, and there should be an arrow like that. There we go. And then the two block system before the collision, well, if I've got 6 this way and 2 that way, then that gives me 4 total. 1, 2, 3, 4. Momentum is so nice. You just add them up. They're vectors. There you go. Now, if this is the momentum before the collision, this is the momentum after the collision. Same thing. 1, 2, 3, 4. Boom. There. Done. Easy. Part 2. During the time interval 0 to t to tc, a force is exerted on block 2 by block 1 along the x direction as a function of time. So this is while the collision's happening, and there's how the force goes. Okay, weird, but that's fine. To me, this would signify some sort of simple harmonic motion. It turns out to not be the case in this problem, but when I see this, I'm thinking simple harmonic motion. A is a positive constant, and F max is the magnitude of the maximum force exerted on block 2 by block 1. Derive an expression for F max. Express your answer in terms of M, V0, A, Tc, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference section. So I'm going to do that in this section over here. It's going to take a little bit of space. So this is for part A2. And the fundamental physics principle they're going to want you to write down is the impulse momentum theorem. So integral f dt equals change in momentum. And we're talking about block 2 here, so I'm going to flip it over again. We're exerted on block 2 by, by block 1. So all these calculations we're going to do are going to be about block 2. So we're actually finding the change in momentum of block 2 over here. So in order to do that, we have to go on a little side quest. We have to find the change in momentum of block 2. That's going to be its final momentum minus its initial momentum. And then we need to do another side quest because to find the final momentum of the block, we need to figure out what's the final speed of the block. We have the initial speed of the block, but we need to find the final speed of the block. So extra side quest over here, we're going to do a conservation of momentum. So we're going to say for the whole system, the momentum before the collision is going to equal the momentum after the collision. And that way we're going to find the speed of the blocks. Luckily, they're moving together at a constant speed. It's always best to go back and check. Yes, they're moving with the same constant speed afterwards, so it's an inelastic collision. They're sticking together, so we have the same final speed. That's really nice. So how are we going to do this? Well, before the collision, we had this one and we had this one. So we're going to keep this one in the positive direction. That's 2 mVo minus, or I can say plus negative 6 mVo, because this one's going in the opposite direction. And this has to equal 7, that's the sum of their masses, 7m times Vf. So this is going to be negative 4, I can get rid of the m's, negative 4Vo equals 7Vf. So Vf is negative 4/7 Vo. And the negative just means they're going in that direction after they collide, which makes a little bit of sense. This one's much more massive, even though this isn't going twice as fast. So they're going in that direction. So now we can use this to go back to this one. So the change in momentum is the final minus the initial, and this is just for block 2. So the final momentum is going to be 6m times this speed in that direction still, negative 4/7 VO. And then we have to subtract the initial momentum, which is still in that direction, negative 6 MVO. Okay, and this is going to be what the change in momentum equals. So we're finding that. So then we can move down. I guess we need to do common denominator of 7s. So we'll just keep this one. So this is negative 24/7 MVO plus, this is going to be 42/7 MVO. And when I subtract those, I get, add these together, this should give me 18/7 MVO. So that's the change in momentum of my second block. Now that I've got that, I can work back and figure this out over here. And now I can take this as the function that I want. Just to flip it over again, the function is Fmax sine A times T. So I'm just going to put that in over here. Hopefully I have enough space to do this. And I'm going to integrate from 0 to the collision time. That's what it said to do. Remember, right over here. During the time interval 0 to TC. So that's what we're doing. And we're going to stick this in Fmax sine AT. And that's all going to equal this 18/7 MVO. And I'm going to tell you this does not turn out to be a pretty solution at the end, but it is what it is. So we take the antiderivative of this one and we're going to get minus cosine. We can pull the Fmax out. Fmax. And then this A has got to come out also. And then this is going to be negative cosine AT. And we're going to evaluate that from 0 to TC. And then this once again equals 18/7 MVO. So evaluating this at TC, so let's see, Fmax over A, and then this is going to be negative cosine A times TC minus, and then when I evaluate put in 0 for there, I get 1, so I get minus, well, it's a minus negative 1 actually, so it's going to be a plus 1 because I have this minus, and then it's minus because I'm evaluating at this limit of this interval, so it's plus 1. And that equals 18/7 MVO, and then it's just a mess here, right? So looking for Fmax equals 18/7. Let's see, I got MVO, I have that A, and divided by this business, 1 minus cosine ATC. Wow, okay, so I don't know, that's not that pretty, but that is what it is, so that's that. Okay, and then part B over here says consider a new scenario. Block 1 slides in the positive x direction with a new speed, v1, so that's going that way, v1. Block 2 again is in the negative x direction, so block 2 is still going at VO in the negative x direction. They collide and stick together, thank goodness. The two-block system has a constant speed VO after the collision. So after the collision, they're going at a constant speed VO, which it doesn't really say which direction it's going in, so we're just going to call it VO. So we'll just call it VO that way. Derive an expression for V1 in terms of VO. Now this one turns out to be easy. Begin by writing a fundamental physics principle. Conservation of momentum, initial momentum is final momentum. And then before the collision, we had m times v1 plus 6m times negative vo equals 7m times vo. Yeah, that's it. And now we're just solving for, look, m goes away, and then we get v1 minus 6 VO equals 7 VO. So V1 equals 13 VO. And that's it for part B. So that's pretty easy. I think that's a very doable problem.